so on and so forth. So the last 2 weeks I drafted out topics that build up from the start, that's from fundamental ideas, and build up into more complex ideas. So this is the scheme of work that I'll be working on for the next 2-3 months, or even less, depending on how often I post videos on YouTube. So the first thing we're going to be looking at, so this is for math. Also, I'll be doing videos on physics, but the scheme for physics is quite small, perhaps 4 topics, which will include thermodynamics and electrostatics, as well as perhaps atomic and nuclear physics. So for math, we're going to start with trigonometry. So we all know the base. I'm suspecting that most of my subscribers know the basics of trigonometry. I can't start teaching you what sine is and what cosine is. So what I'll start from, I'll start from giving you the domain of the angles within any quadrant on a plane, for example. Because this is trigonometry for 2 dimensions. You can't talk about trigonometry in 3 dimensions, except when we get to spherical and cylindrical coordinates. We're talking about angle made by a particle in space, and the angle between that and r, where r is given by x squared plus y squared. Well, it's not the equation of a circle. It looks like it, but it's not. So we're going to be looking at things like that. We're going to touch which of the trigonometric identities are positive in the first quadrant, second quadrant, third quadrant, and fourth quadrant. And also take notes, when we get to 3 dimensions, we'll be talking about octants, because in 3 dimensions we have 8 octants, not quad. We lose the idea of quadrants and we go to octants. So after that, we'll be looking at binomials and coordinate geometry. And if you have a little knowledge about coordinate geometry and trigonometry, you will know that coordinate geometry builds up from trigonometry. For example, I'm pretty sure most of us know the equation of a line, which is giving us y equals mx plus c. We'll see how many ways we can write the slope. We can write the equation of a line in 2. Note that it's in 2 dimensions. So we can also write m to be tan of an angle, where the angle is the displacement from the origin of the x-axis to where the line is. And then I will try to relate this to vector, talk a little bit of vector functions. So I'll try to relate this to vectors a little bit, and yeah. So if I'm talking about simple topics, not really simple, like fundamental ideas, I'm going to be building them up, like just give a brief story. So as I was saying, we're going to be building up these ideas. Most of what I'll be talking will be advanced. I wouldn't be given the equations, just talk about it for fun. So after coordinate geometry, we'll be looking at binomial series. So after that, we're looking at binomial series. Take notes, I did not mention binomial expansion, because if you're only talking about binomial expansion, then we're talking about just expanding 2 variables that's raised to some power. And then I will give you this formula. It's derived from something called the Taylor series. But I wouldn't be showing you the basics of Taylor series. Maybe after we finish the scheme, I'll enter, because I want to do a little bit of plane geometry. So I'll give you this formula. It's given as the binomial series is given us sum of infinite terms from 0 and 1 to infinity of 1 plus x to the power k. This is implicitly written, but there's a way to explicitly write it. So we have to be able to derive the equation for this term. We're going to look at convergence and divergence. of this series and when it's diverging, when the series, what the values of k will be for it to diverge, and what the values of k will be for it to converge. So that's for that. After binomial series, and take note in our coordinate geometry, we're going to be talking about rectangular and polar coordinates. So when we talk about rectangular polar coordinates, it's going to have to link to something we're going to do next called complex numbers, because it's not possible to understand complex numbers without the basics of polar and rectangular coordinates. So we're going to have after complex numbers, we're going to be talking about a lot of things in complex numbers. We are going to look at the applications of complex numbers. Yeah, this is the fun part. We're going to look at the applications of complex numbers in AC circuits. How to not deriving the equation of the we're going to derive the equations of the impedance of a circuit. Impedance, voltage and all that stuff. But we're not going to be using complex numbers to derive it. What I'm saying is that we are going to be looking at how to derive those equations using the idea of complex numbers. So in complex numbers, we're going to be looking at the So after complex numbers, we're going to be looking at area of a function by Riemann sum. Some people call it Riemann, but I call it Riemann. It doesn't matter. So we're going to look at area of a function by Riemann sum. Because basically, Riemann summation. Basically, we know that Riemann sum, area under a curve or area of a function is always given by the integral. But we're going to look at how the basic fundamental idea, which is a little more ambiguous than using integrals. So we will know how Riemann sum actually leads to integrals. So how to actually find the area given by a curve within a closed interval without using calculus. And afterwards, we're looking at area of a function by integrals. I also have to mention somewhere we're going to talk about improper integrals. The reason why we have to talk about improper integrals is because part of what I'll be doing in physics needs a little bit of improper integrals, such as electrostatics. We're looking at how potential difference between two points separated by very little distance. So we're looking at the potential difference there. We're going to need a little bit of improper integral. After that, we'll look at volume types. We're going to look at types of functions. After types of functions, we're going to look at volume of rotated functions. After that, we'll look at disks that's under volume rotated functions. We're going to look at disks, washers. We're going to look at cylindrical shells for volume. After that, I introduce you to vector functions. So So, and yesterday night, I think I'll be able to. I'll see if I can show you guys at the end of when we finish on this topic. Yesterday night, I was working on some hypothetical idea in my mind before I went to sleep. Like, is it possible to actually link cylindrical shells for volume and disks and washers? It turns out that you can, because I was able to derive the equation of a sphere, of a hemisphere and a sphere, from disks. And I had this idea that what if any function, any given function, starts from the origin, what's going to happen to the function? Well, is it going to be the same thing as cylindrical shells for volume? Because the equations are quite different. What I came up with is, okay, I don't want to go into details now, but I came up with this formula. I was able to derive the equation of a sphere using this. I didn't know, it was just a hypothetical idea. I used the same idea, but it was a little more, mind-bending, and I used it here, but it worked. So at the end of it, I came to realize that you can actually link these two equations together, except only when the function starts from the origin. I came up with this idea that the ydx, I'm actually still trying to decipher what this means, because I have it on my phone as a note, the ydx equal to y divided by 2x. I'm still trying to understand, because what I expected was that if I solve the equation for the ydx, I was supposed to go back to the original idea of calculus, that the ydx is equal to y over x. But then I got something strange. It's y over 2x. I was still trying to decipher what this actually means, y divided by 2x. If I do, I'll tell you guys. I actually sent it to some of my, should I say, mathematicians friends I have in Nigeria, to show them it's real good, because, well, this only works for if the volume or if the function starts from the origin. So after this, we're going to be looking at introduction to hyperbolic functions. What we're going to be doing in introduction to hyperbolic functions is we're going to be looking at the trigonometric identities of hyperbolic functions, because in hyperbolic functions you lose the idea of sine, cos, tan, sec, cot, cosec. You start having shine. I like to call it shine, cosh, tansh. Funny names, but that's not the right. I just like to call it that. I don't know why. So you have things like hyperbolic sine. Yeah, hyperbolic sine. So it's written as sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosec, hyperbolic sec, hyperbolic cot. There's something I want to do in trigonometry. It has nothing to do with hyperbolic functions, but I would like to show you a proof of, how when you have cos x plus y, I would like to show you a proof of how cos x plus y is giving us cos x, sine y, the whole formula. I would like to show that using a circle. It's not really, I'm not sure I'll do it, but like if I have the time to sit down and draft the proof, then I'll do it for you guys. So I'll show you how to actually derive these things. Most of the identities I will do in trigonometry, I will derive them. Most, not all of them. So I'll do introduction to hyperbolic functions, do their derivatives, chain rule, I don't know why, anyway, chain rule and so on and so forth. After that, we're looking at vectors. And really, in vectors, in vectors there's a lot of physics in vectors, because
we're going to be looking at standard basis vectors and brackets. We're going to relate it to trigonometry, equation of a line, and so on and so forth. After vectors, we're going to be looking at parametric equations. And we'll see the relationship between parametric equations and vectors, because if you understand the meaning of what parametric equations actually mean, you will see that parametric equations are vectors. After I finish parametric equations, and then there'll be a special day. I don't know if anyone has come across something called the Fibonacci sequence. We're going to derive special day. It's just going to be like a 10 minutes video on that day. Derivation of the nth term of a Fibonacci sequence. Fibonacci sequence. After that, that's all we're going to be doing that day. After that, we'll look at three-dimensional equations such as equation of a line and you see that the equation of a line in 3 dimensions is a parametric equation, because we're going to link that to, after we do equations of spheres, something called parallelepiped, because by then we understand what vectors it is. We look at what the parallelepiped is, 3-dimensional shapes, and so on and so forth. After that, we look at 3D equations. And then after that, finally, introduce you guys to vector functions. Not just vector functions, introduction to vector functions and relationship. With parametric equations. You'll see there's a very huge similarity between parametric equations and vector functions. After that, maybe I'll do plane geometry. Plane geometry will cover lines, intersecting lines, parallel lines, circle geometry, and yeah, so that'll be that for that. Thank you very much. Subscribe and like the video. Thank you.